University nowadays among the 15 universities in Ethiopia, and it's labeled as the first generation university. There are generations in our labeling. So University of Gondar is it trained all health professionals from medical. We have social science, business and economics, veterinary medicine, engineering. This program, I invited staff and students from health, from medical faculty, College of Medicine and Health Science, and my colleagues. I think I can see lots of my colleagues attending, and there are also staffs and students from College of Informatics, including computer science, information science, and others. I also invite from natural and computational science, mathematics and physics, from agriculture, I think. Hopefully, the participants would be from, most of them will be staff, and but I think lately I invited master's students who are interested to join. For your information, we have a lot of PhD program, specialty, subspecialty, master's program, and undergraduate program. I think. Thank you, Tasfai. I think this would be very enough. Just a very brief introduction.
Bahar Dar University, as Prof. Taddasa said, is a department. Thank you so much.
Very good, excellent. So next is Bahar Dar Deborah Marcos. If anyone there. Is there anyone from Deborah Marcos? Is there anyone? You can unmute if yeah, go ahead.
That would be better to have the authority to mute all the participants, otherwise it will not be
Yes,
easy to follow you.
Yeah, I can mute all of them.
Just mute, and when someone wants to speak, just unmute him. That's better.
Yes, I can do that.
Yeah.
Okay. If anyone from Deborah Marcos, unmute yourself and then go ahead. I just mute everyone. Unmute yourself and then from Deborah Marcos. I don't think anyone there. So.
Oh, hello.
Yes, go ahead.
Yeah, thank you very much for your invitation. Deborah Marcos University, one of the participants of this training. As Bahar Dar and Gondar University has said, university has also statistics, chemistry, physics, mathematics, health, medical, and health science colleges. I hope the training will be enjoyable.
Very good. We lost you. Let's continue with Deborah Tabor, if anyone there. No one there? Okay, let's continue with.
I've been doing in one way or another is in the health sciences area. So I get data from, clinical areas, clinical variables, genomics, which is big genetics data, could be environmental, and so on and so forth. So there's diversity in the data that now we get. And also complexity is another big issue. So it's not like very nice and clean data that comes to us. It's a very complex, sometimes unstructured data. It doesn't even have structures that we're used to. So, I can go on and list various good reasons why we need to really do something about these various data sets and learn something from them. So, depending on literature that you read, different people define data science in slightly different way, but the underlying principles to me are very, very similar. So here is my definition. When I say mine, it's just how I understand it. In a nutshell, just simply, yes, data science has both the artistic or the art part, and also it's a science. Also, it's called data science. And in my view, there is also an art to it of converting raw data, which could come from any of these, complex, big, and diverse data sets, into useful information, and hopefully in turn into knowledge. And because there's no one expertise that could do everything, inherently, data science is interdisciplinary or multidisciplinary. But having said that, historically, the two dominant disciplines that lead to data science are computer science and statistical science. In fact, some people say data science is a child of these two disciplines, computer science and statistical science. But as you will hear me say in a few moments, these two are not sufficient. There are a lot more important skills that have to come to the table for someone to practice proper data science. So most of you might have seen such a pyramid going from the bottom, which is data, which is raw data, and using appropriate methodologies and tools, converting that into information and knowledge, and hopefully finally with context and experience, turning that into wisdom. So this is a well-known hierarchy or pyramid, which goes by the acronym DIKW, D for data, I for information, K for knowledge, W for wisdom. In fact, some now say the world's most valuable resource is no longer oil, but data. And I think that is not an exaggeration. On this picture, all of you will recognize this big, gigantic business: Amazon, Microsoft, Google, Facebook, and so on. These are very, very rich companies. And it's not because they went to Saudi Arabia or other oil-rich countries and took advantage of that oil, but they managed to use data and convert it to something that's very important for their business. So now I know people attending this workshop today come from a variety of background. But really, data science can help regardless of your domain or subject matter area. So this, to me, is really the takeaway message is, as long as you have data, using the principles of data science that Professor Rao will be starting teaching you today, and there will be, as I said, a follow-up, and Professor Tesfaye and I have been discussing this the last few months, that our hope is going forward, myself and there are other Ethiopian statisticians in the diaspora that are willing to collaborate with you all and make this a more recurrent workshop rather than just once and then leave it at that. So to me, this is the key. So data is now considered the new oil. Okay, so that's really a brief introduction of what data science is all about. Is just using data and converting it into insight, into knowledge, transforming it into useful information. So what does data science entail? So there are, these are the steps that I'm gonna go through, which I'm sure at least statisticians in attending this workshop will be very familiar to. So the first thing is asking the right question. No amount of sophisticated statistical approach, data science approach, can answer a question if the question is not the right question. So that underlines the importance of working closely with subject matter expert. So if there is a question or around some sort of cancer, it's so important to work with expertise from that area. Some of you are probably from plant science, animal science, business, engineering. It does not really matter. Knowing your subject matter is key. So you have to ask the right question. Some of you may know the famous John Tukey. Tukey was a well-known statistician, considered one of the fathers of statistics. One of the things he said is it's much better to have an exact question and an approximate answer than the other way around. So there is no benefit to trying to get an exact answer to an approximate question. So try to invest your time to refine the question that you are asking. That's number one. Once you have the question very clearly laid out, then you need to acquire data. So data may be already there. Maybe it's in the public domain or something that you have collected in your own field. So think of what data can I use to answer the question that I ask in step number one. So then there are a few steps: processing and cleaning the data, integrating, storing, and some sort of descriptive initial investigation and some exploratory data analysis. Speaking of exploratory data analysis, in short, EDA, again, Professor Tukey is one of the prominent statisticians who has contributed in this area. So it continues, and once you have some idea, some insight from that exploratory analysis, you'll have to choose one or several potential approaches, statistical models, algorithms. So this is where now Professor Rao will be walking you through. So you will see, depending on the question, depending on the data type, he will show you the various models and algorithms. And hopefully in part two, you'll learn a lot more, advanced data science techniques, some people call it machine learning, statistical learning, or statistical modeling, and AI, artificial intelligence, and so on. So I'm not gonna really go. I have sent these slides. I think Professor Tesfaye shared, I don't know, 5 or 6 slides. So, but these are the kind of steps that you have to keep in mind. And as Professor Tesfaye said, Tesfaye, Professor Rao, myself, Tadassa Awuka from Gondar University, and a few other people submitted a major grant proposal to the NIH, which is the National Institutes of Health, the primary funding body of the United States, trying to, hopefully, if we win that grant, to establish a graduate program at Gondar University. And one of the things that we added in that proposal is our approach will be this circle that you see here, because it goes by an acronym PPDAC, which stands for, you need to have a problem, you need to plan carefully in terms of what sort of things to measure, you have to be careful about the proper study design, collecting data and so on. Then you have the data, you go on through analysis, you come up to some conclusion, and this circle will be iterative. So that's how research, is traditionally done. And there is nothing unique about data science other than the fact that we might have some, advanced algorithms and methods, but the principles are very, very similar to what we're used to. Okay, so where am I? Oops. So I believe this is my last slide. Just to show you, earlier I mentioned the 2 major disciplines that kind of led to data science are computer science and statistics, but that's not sufficient. So I like this this cartoon or this illustration from this company. What's modern data scientist or if you want to be a data scientist, what sort of skill should you have? So as before, you'll see here math and statistics, and on the right, programming, database. So these two are kind of computer science and statistics. But then here is the key now, the domain knowledge and other soft skills. So the domain knowledge is what I was referring to as subject matter expertise. So those of you from health sciences, you bring that domain knowledge. Those of you from plant science also have your own domain knowledge. That's critical. And there are some, other soft skills in terms of understanding specific issues. And equally here, on the bottom right, is communication and visualization. In data science, it's critical to be able to visualize data and also trying to communicate to your stakeholders. So one of the things here is, I'm sure if you have a copy of these slides, you can read them, storytelling skills. So see, that's what I'm saying. It's not just like you use R or you do some math and write some equations and you are done. No, you have to be able to tell a story. So what did you learn and what are the implications? So starting with the right question, you go through that loop, and at the end of the process, you must be able to, pass what you learn from the process of data science. So our packages are listed here, and now you are going to be learning lots of R starting today by Professor Rao. So I think without further ado, I will stop here and pass it to the main session today, which is how. So to recap, I told you what data science is about briefly, why do we need it? And I could say, when do you use it? Where do you use it? Who do you use it for? So the 5 W's, what, why, where, who, when. But I think the key is now the H, how. And that's what Professor Rao is going to be doing. So I will stop here. Thank you.
Excellent. Thank you so much, Joseph. It's an excellent way to speak to Professor Rao. I think one thing I just want to mention is that you may come from different
of the ceremonies. Okay.
I'm trying.
You are the master of the ceremonies. Okay.
Thank you.
You make sure that the proceedings go smoothly, and pausing, breaking, recording, you are in charge, right?
Yes. Okay. Yes.
Okay. I want to share 2 things. Okay. One is my notes on the workshop, and the other one is R console along with the editor. Okay. This is kind of a hands-on experience workshop. The whole idea is I'll plop up some data and then start typing about R functions, and the people who are attending this workshop can also use their own R console. You can mimic me so that you can learn everything on the spot. Okay. Maybe there could be some frustrations, some coding is not working, at least to make an attempt. And then we keep the dialogue on through chat box. Okay. So let me share screen. One is, okay. One is I want to share my R console along with the editor. Okay. Are you able to see my R console?
We see your R, but we don't see the notes and others. Maybe you can share the screen so that you can choose from files.
Okay. So it has come on my screen. Let me see.
What you shared is just the R.
First, what I did, I clicked on share and then I clicked on R console, right?
If you share the screen like you did yesterday.
Okay. So should I do stop sharing now
Yes.
and again start all over?
Yes.
Okay. All
Stop
right.
sharing.
Okay. Let me try again. Share screen and then okay. Let me try again. How about now? Test. Are you able to see my console?
Yes, we see only the R.
Okay, that's fine.
Okay.
You're able to see my console. And the next thing I would like to do is, okay, I would like to share my notes. Okay. So let me click on new share. Okay.
No, I think you need to share the screen, the entire screen, so that you can select which file,
Okay, okay, I see.
Not one file at a time. If you share one file, you only see that file. You can't share the other one.
Okay. I mean, this is my entire screen, right? I can see, okay, select whatever I want. I see, okay. That one and that one. Okay. Okay. And can you see my notes?
Yes.
Oh, very good. And in the background, I have R console. Can you see that too?
We can't see, at least I can't see the background, but can you show, open the other one, like here? Can you open? Maybe if you see it, that's good.
Okay, let me try again, just 1 minute. Okay, new share. Let me do, click on it and then click share. Can you see the console now?
Yes, yes. You can move from, like, you can do this way. Whenever you can shift one from the other.
Okay, so you can see my console and I'm going to click on my notes too.
Now we see that your note is there. That's right.
Okay, both are there. Very good.
Yeah.
Very good. So I'm going to start something on the workshop. Then I'll go back to R console.
Excellent.
Okay, good. And let me see. Okay, all right. So good morning. He's a good morning. It may be good afternoon to you guys. Okay, because you are ahead of us. So I'm going to do data science basics and R for all. And this is the first day of the workshop. And Joseph made an excellent introduction, what data science is about, and how a data, he also presented the makeup of a data scientist. Who is a data scientist? So that's a very good presentation. And I'm going to work on various features of data science. And I work on a number of interesting data sets. And the rest of them were sent home to recover. What happened to the 260 patients? Some of them were admitted into ICU, intensive care unit. Again, discovery. What factors influenced the medical doctor to send him to ICU? Okay, that's fine. And then now some patients are there in ICU. Roughly about 100 patients were sent to ICU. And from ICU, some of them died. Now the question is, what factors made the patient die? So the investigation goes at 3 levels. Who got to go to the hospital? All of them are infected. Who got to go to the hospital? Once he's in the hospital, who got to be admitted into ICU? Once he's admitted into the ICU, who died? So 3 levels of investigation. So we are working on that particular data. And of course, when you try to submit the article for publication, and the referees and the editors say, this is a small data, 689. Oh, nothing much. Okay. So what happened was my collaborators, Dr. Mendy and Dr. Mora, they set about collecting more data. Now they have 15,000 patients. 15,000. All were tested positive for COVID-19. And of course, Dr. Mendy tells me he has got the data from the same hospital. Patients are coming from the tri-state area, Indiana, Michigan, Indiana, Kentucky, and Ohio. And whenever you have that kind of a data, and boy, logistics is a problem. Cleaning up the data takes a heck of a lot of time. And is cleaning the data. He has been working on it for the past 2 months to make sure that the data is something presentable, clean, and ready for analysis. I'm waiting in the wings. I told him, I don't get involved in the cleaning. You do it and give me the good data. Okay? All right. You know, you look at regression methods lie at the heart of data science. I will strive to provide you a solid background in regression core. The theme follows the pattern: data, then postulate a model, and use R code to analyze the data, get the output, discussion, and so on. Okay. And of course, now the date is fixed. I will embark on data science techniques to extend and enhance your knowledge base acquired from these sessions. Okay. I mean, it's very ambitious. I don't know how much I'll be able to cover today. Talk about introduction, history of regression, importance of regression, and then especially simple linear regression. I'm going to put a lot of emphasis. Okay. Diagnostics, a specific example, talk about a confidence bands, clinical importance, and have a very fascinating data called mammals data, and what transformations could do to make the data more analyzable, lessons learned, talk about a categorical predictors, multiple regression with a categorical predictor, and a multiple regression unbound, multivariate multiple regression. Okay. You know, you ask why regression? The name itself is a misnomer. There is nothing regressive about the methodology. But anyway, the phrase was introduced by a famous geneticist from England, and the name got stuck. You can't shake it off. There was a paper, interesting paper, published in a New England Journal of Medicine. Nicholas Horton and Suzanne Switzer. What did they do? They looked at the articles published in the journal from January 2004 through June 2005 for statistical content in the article. Okay. You cannot publish an article without the statistics. Okay. Any article with a method section qualifies for further examination. They identified several broad categories of statistical methodology and counted the number of articles which used specific categories. This is only, they have been doing it, not just once, couple more times, different periods. I want to share you, this article is published in a New England Journal of Medicine. Okay. Statistical methods in the journal. When you say the journal, they mean New England Journal of Medicine. Okay. 2005. So what they did, they presented a table like this. So they conducted the survey at 3 different time periods: 78, 79, 89, and 2004 and 5. Okay. No statistical methods or descriptive statistics only. Okay. Let me show you okay. Let me show you something. You know, total number of articles is scrutinized in each period. The first period is 332. The second period is just one whole year, 115. And the third period, 311 articles. Okay. The first and third covers 2 years, and the middle one covers just 1 year. So those are the articles surveyed. Okay. And out of 332 articles, 91 of them has either no statistical methods or maybe only some simple descriptive statistics, which amounts to roughly about 27%. Okay. And look at this t-test. Okay. Everybody is familiar with the t-test. Testing a 2-sample problem. It could be testing the equality of 2 population means and so on. So if you look at the t-test, 44% of the article in 78, 79 used t-test. And the percentage came down to 39 in 1989. And the percentage came down further in 2004 and 5 to 26%. You know, the popularity of a t-test is decreasing. Okay. Non-parametric test, epidemiologic statistics, Pearson's correlation, and a simple linear regression, you know, is simple. That's why it's 8%, 9%, and 6%. Analysis of variance, and is more or less stable. And apply transformations to extract better signals. Okay, not so much. Non-parametric correlations. Okay, and survival methods. At the beginning, early on, only 11% of the articles used survival methods. In the next period, it rose to 32%. And the latest period they surveyed, 2004 and 5, it rose up to 61%. You know, I give a class on survival analysis. Okay. Where do you get a survival analysis? It's from clinical trials. If you look at the clinical trials currently at the moment, you might ask me, how many clinical trials conducted all over the world? The estimate is about 360,000 clinical trials are going on now. Children's Hospital conducts quite a few. University of Cincinnati, yes, quite a few, right? And 80% of the clinical trials are conducted in the United States. And the remaining 20% is spread all over the world. Okay. Clinical trial is bread and butter of testing new medications. Is a gold standard for testing. And to look at its popularity as a statistical method, 61% in the latest period. And you look at a multiple regression, it started in a very humble way. Only 5% of the articles used multiple regression, which improved to 14% in the next period. And if you look at the latest period, 51% of them had a multiple regression. Okay. And adjustment and standardization, multi-way tables is more like a contingency tables. And look at a power analysis. What is a power analysis? It deals with the sample size calculations. I'm planning a study. What should be the sample size? That's a fundamental question in every clinical trial, in every funded project. Okay. It started moderately the first period and the second period and rose roughly about a 40% in the latest period. Okay. Cost benefit analysis, sensitivity analysis. Okay, nothing in the first period, nothing in the second period. And you look at the third period, 2004 and 5, 6% of the articles deal with the sensitivity analysis. You know, I'm working on a project on sensitivity analysis. Okay. You look at a human being. Okay. What do you think about his age? You talk about a chronological age. You know your chronological age. When you were born, sure. From that you can calculate how old you are. That is just one age. But there are some hidden ages. Another one is, one age is called physical age. Physically, how old you are. And another one is mental age. Mentally, how old you are. Okay. A test, it says to start my video is already on, isn't it?
Yes, it's recording.
Okay, it's already there. Okay. Another one is mental age. Okay. Typically, for a human being, chronological age, physical age, mental age, they go in coordination. I know a case. Okay, a case in India is a physical age is 4 times of his chronological age. When he was a 5-year-old boy, he looks like a 20-year-old man. So well developed already at the age of 5. And you know, in marriage, you cannot marry until you are 16 years of age. But he's a 5-year-old boy, chronologically, he looks like a 20-year-old man. And the parents asked the governor to provide a special permission for him to marry. So he married at the age of 5 and he got some children. And when he was about chronologically 20 years of age, he looks like an old man, 80 years of age. And soon after that, he died. It's rather unusual. Okay. Now we are talking about methylation age. You know what is methylation age? You look at the environment, the pollution. The pollution influences your age. Okay. And probably, you know, I can give examples. You know, I live in America, you know, and look at my brother, my younger brother, he's already dead. My older brother, of course, he died about 5 or 6 years ago. Okay. I start thinking about it. How come I'm still living? My siblings are all dying. I thought that maybe the pollution ages you as well. How do you measure the effect of pollution on your age? And the scientists have discovered to calculate what is called methylation age. The methylated sites in your DNA get influenced by the pollution. Okay, so they've developed a technique to calculate the methylation age when the child is subjected to pollution. And typically, what I see in the data, the methylation age is usually greater than the chronological age. That's what's fascinating, right? And they asked me to do sensitivity analysis of the data that came through. I'm currently working on it. Repeated measures, missing data methods. Okay, that's a big thing now. Non-inferiority trials coming from clinical trials, ROC curves, diagnostic test, resampling, principal components and cluster analysis, other methods. Okay, and of course there are papers on genetics and some papers on meta-analysis. What I understood from this, the degree of sophistication in the uses of statistical methods is on the rise over the years. That's what it is. Okay. Okay. The basic idea behind the modern version of regression is to find the line of best fit for bivariate data. You have two quantitative variables typically measured on each subject in the study, an X and a Y. You have a subject 1, you take a measurement on X, X1, measurement on Y, Y1. Take a subject number 2 in the study, a measurement on X, X2, measurement on Y, Y2, and so on. Okay? At the heart of the discussion lies two quantitative variables, X and Y, measured for each subject in the population of interest. You can keep an example in mind. What you are trying to do is, you have X and Y. One is response, the other one is predictor. So the argument is X influences Y. Okay. How? Can you put down an equation? Can you find the line of best fit of Y on X that somehow summarizes the information on X and Y? Every model you build is a summary. Remember that. Every model you build is a summarization of the data. Okay. So let us look at one example. So keep this example in mind, and this example keeps up again and again in the clinical practice. Okay. You look at all healthy boys in the age range from 12 to 14 years from a geographic region. And for each boy in the population of interest, you measure the height and you measure FEV, forced expiratory volume. What it means is, there is a tube, you blow into the tube for about 70 seconds, I believe. You blow into the tube for about 70 seconds and measure the volume. Measure the volume of air expelled. Okay? So this example is very much relevant to pediatricians. Okay. I will talk about it, why it is so important to pediatricians. We take Y to be the dependent variable, or you can call it as the outcome variable. Okay. And we take X to be the independent variable. You can call it as a predictor, or you can call it as a cause. Okay, you can call X to be cause and Y to be the effect. We are trying to build a causal model connecting the cause with the effect. Okay. We take a random sample of n boys from the population and measure X and Y for each boy in the sample. That's how we have the bivariate data. The basic thrust of inquiry is to quantify in the form of a model how X influences Y. Okay? This is anecdotal. The taller you are, the more air you expel. The taller you are, the more FEV you will have. It's a common sense. But we want to nail down the relationship. You want to nail down the relationship into a mathematical model. When you do that, that model is a summary of all the data you collected. In one line, you can explain the relationship between Y and X. Okay? Okay. So the line of best fit through the data falls into the ambit of the inquiry. Structurally, the line of the best fit is of the form Y is my response, my X is my predictor. This is the equation of a line where A is the intercept and B is the slope of the line. Okay. Legendre, the French mathematician, way back in 1805, and Gauss, a German mathematician, in 1809, introduced a method of least squares to determine A and B. So, when you talk about, you will have the data. I'll show you the data. You will have the data. Okay, height and FEV, height and FEV, and so on for a bunch of boys. Okay, you can plot the data as a scatter plot to find out what kind of a relationship persists between X and Y. I want to draw a line through the data. You can draw millions of lines. Okay, so you need to introduce an optimization criterion to find the best line. Okay, so that's what it is. Okay, and they introduced the method of least squares in the context of astronomical observations. So they wanted to trace how the planets orbit around the sun. Okay, they can only observe the position of the planet at certain times, and using that kind of a data, they need to model how the planet is moving around the sun. They need a method. They need a method to build a model about the orbit of the planet. So they wanted to trace the path of a planet around the sun in our galaxy. The method of least squares endeavors to find A and B, okay, minimizing something called an expression like this. Yi is the ith data point, Xi is the X value for the ith subject, and the model is Yi equal to A plus Bxi. Take the difference, okay, and you can choose any A and B you want. You can choose any A and B you want, and you already have the data. You can calculate f of AB. Okay, this is just a little bit of mathematics, but there are millions and millions of A and Bs. So what you do is find that A and B such that this is meaningful. Okay, you want to find A and B such that a plus bxi comes very close to yi. You look at the difference, square the difference, and add overall observations and try to minimize with respect. Okay. Anyway, so this is a method of least squares, is a classic, and the difference is squared. Why this? Why did they take the square? Because it's a nice calculus function. For what values of a and b, this is minimum, you can use the calculus. Okay. Differentiate this with respect to a, differentiate this with respect to b, set them equal to 0. You have two equations and two unknowns. Solve for a and b. Voila, you got a solution for a and b. So let us not worry too much about it. One could draw millions of lines through the data. Any line can be written mathematically by y equal to a plus bx for some a and b, and characterized by two numbers a and b. Find a and b such that the line is the closest to the data. Okay. Anyway, okay. So why am I spending so much time on this? Every software will give you the line of best fit. The criterion for minimization is important. Later, I will talk about ridge regression and lasso. These two methods are very much in vogue when it comes to model selection. The methods tweak the minimization criterion for building tight and lean models. Okay. Hopefully, maybe on the fourth day, I'll talk about a lasso. Okay. Gauss published a paper in 1821 developing the method of least squares, including a version of so-called Gauss Markov. The term regression was coined by Francis Galton, a cousin of Charles Darwin, and is an accomplished 19th century scientist. Okay. It was coined by Francis Galton in 1894 to describe a biological phenomenon. The phenomenon was that the heights of descendants of tall ancestors tend to regress down towards a normal average. A phenomenon also known as regression toward the mean. He also presented data on sweet peas. Okay. Okay. And what he did in this case, for any p, diameter of a parent seed in units of 0.01 inch, and the diameter of a daughter seed in units of 0.01 inch. The data are available on internet. Galton also recognized as a father of a statistical science. Okay. Anyway, so this is a little bit of history and a little bit of mathematics. Okay. And in the 1950s and 60s, economists used electromechanical desk calculators to calculate regression. Okay. You know, you have to do optimization. And in the case of a simple linear regression, it doesn't take much time. When I can use my desk calculator, my calculator to calculate A and B R. Okay. Before 1970, it sometimes took up to 24 hours to receive the result of one regression. Suppose you have 10 predictors, one response variable. Again, you apply the method of least squares. You have to solve 11 equations in 11 unknowns. You need to invert a 11 by 11 matrix. And the desk calculator might take about 24 hours. But now computing revolution, it's all done in a jiffy, less than a second. Okay. Now the subject of regression made huge inroads in science and arts. Tremendous advances both on the theoretical and computational sides, okay, have been made and continue to be made. I want to share my knowledge on this subject with you in this session. Okay. Regression models essentially bring out cause and effect of observable phenomena. They are also called causal models. One identifies the cause, the causal and effect variables, and regression enshrines the relationship in the form of a mathematical model. Okay. Simple linear regression, okay, basic setup is the response variable is quantitative and the distribution of y depends on a single predictor x. Okay. And what is the model about? For every given value of x, you can keep x as a height and y as FEV. For every given height, the distribution of y assumed to be normal and the mean is a linear function of x. Some beta 0 and plus some beta 1 times x, and the standard deviation sigma is positive for some unknown parameters beta 0, beta 1 and sigma. Normality assumption and the standard deviation sigma is the same for all x, homoscedasticity. You know, I'm sure you have fitted simple linear regression models to data, but the meaning behind it is pretty deep. We are looking at the population, okay, and you're looking at XY values, and you break the population into subpopulations. Look at the subpopulation of all those guys with a fixed value x. When x is fixed, what can you say about y? It may not be a constant. It won't be a constant. And what is the distribution of y for fixed x? Normal distribution, and the mean depends upon x. Some beta 0 plus beta 1 times x. And the distribution has a variance. Maybe call it as sigma squared. Okay. You change the x, the mean is changed. And sigma squared becomes unchanged. That's a simple linear regression model. In fact, this is a general form of any multiple regression model. I don't know, just this is all fundamentals. Look at the subpopulation of all subjects with the same value x. The y value varies from subject to subject in this subpopulation. Variation is present in the y values of the subpopulation. The mean is a linear function of x. The distribution is normal. The standard deviation remains the same no matter which subpopulation we are looking at. In other words, it does not depend on it. Okay. Let me look at this concrete example. Okay. And what I'm looking at is all healthy boys in the age range 12 to 14 years. They're all middle school students. And for each healthy boy, you measure height and you measure FEV. And the goal is explore the connection between X and Y. Why do you want to study this problem? This is of clinical importance. I'll talk about clinical importance later. The taller the boy is, the larger the value of FEV is. Common perception. And I want to nail down the connection. Okay. X is equal to effect and Y equal to cause. Develop a causal model. I propose a simple linear regression model. Okay. For a given height, Y is normally distributed with mean depends upon X and the standard deviation is the same. for some betas and sigma. So this model has 3 parameters. One can estimate the parameters using the collected data on the boys. Typically, this is how you write a simple linear regression model. And the same form goes through for multiple regression models. So y equal to beta 0 plus beta 1x, that's perfect. Okay. And this model is contaminated by noise, which is a normal distribution with a mean 0 and standard deviation sigma. And you collect the data, choose n levels of x, and how one chooses the levels is another area of research. And for each level, you observe the value of y and just draw one observation. Why do we need the assumptions? Normality and homoscedasticity. First of all, for examining the impact of x on y. We test the hypothesis of skepticism. Okay, remember, beta 1 is a slope. You test the hypothesis of beta 1 equal to 0. This is skepticism, but the predictor has no impact on the outcome y. The healthy skepticism. For testing, we need a test statistic based on the data and a test built on the statistic. Okay? The distribution of the test statistic used in this connection requires the assumption. Okay. One can check the assumptions before testing the impact of x on y. And no, because we are drawing only one observation of y for each chosen level of x. Okay. If we can get 20 or more observations of y for each level of x, we can check normality and homoscedasticity. Okay. There are tests available. Normality test, Wilks-Shapiro test, Bartlett test, and so on. All right. This is a theory. Let me skip. And I apply the method of least squares. I have explicit expressions for the estimates of the slope and the intercept. Once I have the data, I can crunch the data and get an estimate of the slope. And an estimate of intercept, you can do it. And you can write down the prediction equation. And then we talk about residuals. Okay. Observed value of y minus the predicted value of y for a given x. Observed value of y minus predicted value of y when x is equal to x. The residuals can be viewed as a sample from the distribution of the error. And how you need to judge how good the model is. The residuals play an important role. Okay. The judgment is based on how close the observed values and the predicted values of y are. So there are a number of tests available: Kolmogorov, Smirnov test, Levinsky test, Wilks-Shapiro test, and so on and so forth. And the graphical procedures are also used. And you can also estimate the variance of the model. They have a very nice explicit expression. Okay. Okay. All right. Talk about the outliers. I'll come to that one. High leverage points. Let me skip that. Let me go to a specific example. Okay. So what is the specific example? Model the relationship between FEV and the height of a sample of normal boys or healthy boys in the age range 12 to 14 years. Here is the data and the R code. So what I would do, I don't want to type the data. I just copy and paste. You can also do the same thing. Okay. And look at, there are 2 columns of data. Okay. And I'm going to copy I'm in Word. I'm going to copy and then let me go to R console. Okay, guys, can you see the R console now? I hope so.
Yes, yes.
Very good. So I'm going to copy the data. So edit and a paste. Okay. You know, the height is measured at 4 centimeters intervals. Okay. And FEV is also measured, okay, for each boy of a certain height. Okay. So one of the things you would like to do, I want you to see the data yourself. Okay. This is my data. This is the data on, okay. What I would like to do, I run it. I'm using editor. Run it. I have it here. Okay. And look at what is inside this folder. Run it. And we have, you can also, I'm going to type some basic R functions. How many observations do you have? And what is the R function? The R function is the length. What is the length of the data? Of the data in height. So you run it. That's 12 observations. Okay. And then look at the FEV. Okay. And run it. How do you run it? You go to R console. There are 5 icons. You look at the middle icon. It's like a flapboard. And click on it. Run line or selection. And you get it. And you want to look at what is inside FEV. You simply type FEV. And run it. Click on the middle icon. Those are the data. Okay. So what you need to do is, let me type. These are the data on 12 boys. Okay. And look at the data. Together. Okay. So I would like to introduce a name. Okay. I don't know, maybe let me use MB, just my initials, defined by. The function is data.frame. You put them, these 2 columns of data in a single frame. That's what I'm trying to do. So one column is called a height. The other column is called FEV. Okay. And run it. Done. And you want to look what is inside MB. Just type MB. And run it. That's all it is. Boy number 1, height is 134 centimeters. He blew into the tube. His FEV is measured to be 1.7 liters. Boy number 2 has a height 138 centimeters. He blew into the tube. His FEV is measured to be 1.9. Okay. So we have a data and 12 boys. I tell you, this is a real data. A researcher was given the task of discovering the connection between height and FEV. She collected data more than 600 boys in Michigan. I'm just giving you a subset of this data. Okay, I summarize the data in some context and I give you the subset of the data. Okay, so what do you do? Let me put a query. One minute. I need my glasses. Just okay. Okay. All right. What I'm typing the number symbol. What it means is not R code. This is for your benefit or for my benefit as well. Okay. Explore the relationship between height, which is measured in centimeters, and FEV, which is measured in liters. Okay. The best way to do it is do graphics. Okay. And get us what is called a scatter plot. These are all basic, simple things. Maybe some of you are already familiar with this one, and there may be people you are using R for the first time. It is for their benefit. Okay, do scatter plot. So how do I do a scatter plot? Okay, the R function is plot. Okay, and the first entry first entry is the X variable, which happens to be height. Height is defined already. The Y variable is FEV. Okay, and describe the plot. X lab means what do you want on the X label? What do you want on the X axis? You have X axis and you have a Y axis. What do you want on X axis? What do you want to be typed? You can say that height in centimeters. Okay. What do you want on the Y axis? Keep on typing inside. I don't like that. I want you to see the whole screen. Go to the next line. And whatever you want to be printed on the X-axis, it should be in double quotes. It should be in double quotes. Y lab, you can see FEV in liters. And each 134, 1.7 is 1 point on the graph. Okay. You need to mark this point on the graph. And you can choose the plotting character. Okay. PCH stands for plotting character. You have plenty of choice. There is at least 30 possible symbols. My favorite symbol is 16. A dark circle. Okay. And you can color the plotting character. So the input is color equal to double quotes. Let us use a red. Okay. And you can give a main title. The main title input is main, and the title should be in double quotes. Okay. You can say that scatter plot okay, of data. You can type whatever you want with the double quotes. Scatter plot of data from 14 to, oh, sorry, maybe 12 to 14 years, healthy boys. Close it. The plot begins parenthesis. The first entry is always X and the second entry is Y. What do you want to be printed on the X-axis? Type within double quotes. What do you want to be printed on Y-axis? Type it up in double quotes. What plotting character would you like to have? I chose number 16. And how do you want to paint the plotting character? Red. What do you want to have the main title? Try to make the graph as informative as possible. Okay. Let me tell you thing. PCH is called a plotting character. Okay. And you have a 600 colors available in R. Okay. Another thing I would like to say is the R software is case sensitive. Okay. You type the name height with H in caps. You should follow exactly the same iteration. It's case sensitive. And let me run the plot function. Let me run the plot function. Run it, go to the middle icon, click on it. I got it. Okay, look at X-axis, X label, height in centimeters, and look at the Y-axis, FEV in liters, and my plotting character is 16, which is a dark circle and painted red. And I gave a main title, scatter plot of data from 12-14 years healthy boys. Okay. And this gives you a preliminary understanding about the data. So what do you learn from here? What we are learning? Okay. The relationship seems to be linear. Seems to be a line. The line seems to go through really well. Okay. So the next task will be find the line of best fit. Okay. I talked about the method of least squares, minimizing something, using calculus, and getting formulas for the intercept and the slope. R can do it for you. Find the line of best fit. So let us do one thing, give a name. How to find the line of best fit? The R function is LM. LM stands for linear model. Okay. And what is your response variable? FEV. Tilde. Okay. And what is your predictor? Height. Okay. This is the way you type it up. And remember, the y variable comes first, tilde, then the x variable comes second. Whereas in the plot function, the x variable comes first, followed by the y variable. You identify the data, and data equal to MB. That's all it is. And then you can I want to keep this one. And we are here now, and execute this line, R function. Got it. Okay. And then now what you do, okay, what you do is show me what is inside. You use the R function summary and applied to MB1 and run it. That's the summary. It looks a bit complicated. Okay. I will explain this meaning of each and every thing here, but I want to get estimate of the intercept. And intercept happens to be minus 5.31, corrected to 2 decimal places. Okay. And can you get me an estimate of the slope? And that is 0.05. Will you be able to write the prediction equation? Okay. The prediction equation is my FEV is a response variable equal to estimated intercept minus 5.31 plus and estimated slope 0.05 times and the height. This is my prediction equation. Okay. And the question is, draw the prediction equation on the scatter plot. Okay, it's a very simple training. It's just a beginning. Okay, once you get the hang of it, what the R functions are, I think you should extend it, all the basic training to more sophisticated models. Draw the prediction equation on this one. How do I do that? The R function is AB line. And what is the input for AB line? MB1. Okay, that linear model. And you can choose whatever color you want. Maybe I choose blue. And you can make a line as thick as you want. LWD equal to 2. You might wonder, what is this? Okay. LWD is called a line width. Okay. And the line width equal to 1 is the default. Is the default. And by putting 2, I want a thicker line. Okay. So let me go back to AB line is an R function and run it. Done. Okay. And I want to make this graph as informative as possible when you are writing a paper and you want to include the results of your simple linear regression exercise. You can produce a graph like that. You make it informative. You can type up the equation in one corner. Type up the equation, the prediction equation on the graph. Okay. How do I do that? The function is legend. Legend is an R function. And where do you want to? Okay. Okay. Somebody is asking for a remote control of your screen. A test. Are you? What do I do? Shall I approve it?
What was the question?
Okay. Is requesting remote control of your screen.
Maybe not now.
Okay. So for, I mean, we are recording it anyway. We will send the recording to them.
Yes, that's the plan.
Okay. So I can decline or approve.
I think decline is better.
Better. Okay. Okay. Legend. Okay. Make it the graph as informative as possible. The readers love it. Where do you plan the legend? Top left, top right, left, right, bottom left, bottom, and bottom right. There is plenty of space. Okay. I choose top left. I choose the top left. Okay. And then what exactly your legend? The legend you want to type in double quotes. FEV equal to minus 5.31 plus, okay, 0.05 times height. Double quotes, comma. Okay, I hope you can see it, comma. Then you create a bullet. PCH, my favorite is 16. You color the bullet. Color is equal to, it doesn't matter. I like magenta. Choose the color magenta and close it. So you have two lines here. Highlight both the lines and click the middle icon. We wrote the equation. Okay. And there are number of questions. We can say we are fitting okay, a simple linear regression model okay, a simple linear regression model to the data. Okay. The fundamental question is how good the fit is. How well the model fits the data. That's what you are interested in. Okay. You are okay, right? How good the fit is. Okay. And we read R squared. We read R squared from the output. Okay. Let me minimize this. And you go the output to MB1 and somewhere you see R squared. And R squared, okay, R squared here from the output is a 97.65%. Okay. So what does it mean? R squared 100% means perfect fit. All points, all data points okay, will lie on the line. Exactly. No deviation. And our R squared is 97.65%. It is indeed a very good fit. Is indeed a very good fit, right? Now the philosophy. The philosophy is the model, the simple linear model, is a summary of the data. The model is a summary of the data. Because you have a 12 data points. You may have a 5,000 data points. You do simple linear regression. And the simple linear regression model is a summary of the entire data. You can say that is a dimensionality reduction. Okay. How can I put the whole data into a single equation? Okay. That's the way to look at it. Okay. It's a summary of the data. Okay. And the model has 3 parameters. Okay. One parameter I told you is the intercept. beta 0. Another parameter is slope, beta 1. The other parameter is sigma, the variation. Okay. And the sigma is also estimated. It comes from here, 0.1205. This simply tells you inherent variation, okay, in the measurements of FEV. Okay, how much variation is present. So we got all the three parameters. And the next important thing is, okay, interpretation of the model. Interpretation of the model. What can you say about the model? What can you say about the data? Okay. And the thing is the slope. Slope is equal to 0.05. What does it mean? If the height goes up by 1 centimeter, if the height goes up by 1 centimeter, what happens? FEV goes up by 0.05 liters on average. You can say this is what I call a simple interpretation of the model. So elegant. Okay. You know, you're thinking about height is connected to FEV. I understand. I'm trying to make the connection more precise. I'm building a model. A simple linear regression model is in order. My scatter plot tells me, please go ahead and do it. I did it. The model fit is good. And I got the prediction equation. What is interpretation? Can you say in one line about this phenomena? My one line summary would be, if the height goes up by 1 centimeter, FEV goes up by 0.05 liters on average, there is a 0.05 is the slope. Okay, so that is a very beautiful interpretation, so easy from the simple linear regression model. Okay, the height increases the FEV and you are making it very precise. R squared is so high, 97.65%. Okay, and what else you can do? Statistical jargon. Statistical jargon. People ask, okay, is height a significant predictor is a height a significant predictor of FEV? Okay, can I use a height? Okay, okay. You know, this is a very important question. Okay, this is an important question. For a pediatric, okay, you can say that for pediatricians. Okay. So when you ask for something like that, is it a height a significant predictor of FEV? And we are testing the null hypothesis. The null hypothesis that the population slope is 0. So you're talking about the null hypothesis. Okay. And the population slope is the notation is beta 1 equal to 0. Okay. So what this means is null hypothesis. This means this is a hypothesis of skepticism. This is a hypothesis skepticism. Okay. It means I do not believe height has anything to do with FU. Skeptic. Come on, I don't believe it. Okay. And using the data, okay, this is the core statistical reasoning. Using the data, we have an estimate of beta 1. And which is 0.05. It's only a sample of 12 boys. And the population beta 1 equal, look at the population of all healthy boys in the age range 12 to 14 years. Okay. In the population, there is a connection between FEV, we postulate there is a connection between FEV and height. And we just do beta 1 equal to 0. I don't think there is any connection between height and FEV. But a sample estimate gives a value 0.05. Okay. Okay. So the question is, if the null hypothesis argument, if the null hypothesis were to be true, what are the chances that its estimate from the sample is as large as 0.05. We ask, come on, it's only a sample. You don't expect the sample beta 1 to be equal to perfectly 0. It's only a sample. sampling variation. Okay. If the null hypothesis were to be true, what are the chances of getting an estimate as large as, at least as large as 0.05? Mathematical statisticians calculated this probability. This is p-value. That's the interpretation of p-value. And here the p-value is in a scientific notation 1.80 times 10 to the power minus 9. The scientific notation. What kind of a number is this? Which is very much, and which is very much equal to 0. 10 to the power of minus 9, that means 1 followed by 9 zeros in the denominator, which is very much equal to 0. Okay. And my argument is very simple. If the null hypothesis were to be true, I will not expect to get an estimate of it as 0.05. I don't believe, because it's such a low probability. What are the chances of getting an estimate as large as 0.05? Negligible. Okay. I don't expect such a value to come up, but such a value came up. Such a number arose. Okay. I did not expect it to come up, but it came up. If the null hypothesis were to be true, I do not expect it. I do not think such a number would arise, but it came up. So what I do, assumption, okay, that population beta 1 equal to 0, the assumption beta 1 equal to 0 is suspect. Okay. So the argument is reject the null hypothesis. Reject the null hypothesis. Okay. And statistical jargon, yes. Okay. Yes. Height is a significant predictor of OFE. There's so much is going on. A simple example, try to understand what's going on. Is a significant predictor of FEV. Okay. The one fundamental question is, when do we reject the null hypothesis? In general. Okay. Industry standard when the p-value is less than 0.05. And if you look at the p-value 1.80 times 10 to the power of minus 9, obviously is less than 0.05, you reject the null hypothesis. Okay. I want to tell you something more interesting. Oh, why it's not moving? Let me see. Okay, let me come here. Ah, good. Okay. I would like to tell you something about British nomenclature. Okay. If P happens to be between 0.01 less than or equal to P less than 0.05, okay, say the predictor is significant. If p-value happens to be between 0.01 is between 0.01 and 0.05, say the predictor is significant. If p-value is less than 0.001, but less than 0.01, between 1% and 0.1%. In the earlier case, between 1% and 5%. In the next case, is between 0.1% and 1%. Okay. And say the predictor is very significant. Okay. If P happens to be less than 0.001, less than 0.1%, and say the predictor is very, very significant. Okay. So what happens is basically, okay, you give stars. You give a star rating. Okay, and a significant, a single star. Okay, and it's very significant, you give a double star, and it's very, very significant, you give a triple star. Okay, so if you look at here, height is the output, you look at here, estimate is 0.05. There is something called mathematical statistics, standard error, p-value, and the p-value is reported in the last column, 1.80 times 10 to the power of minus 9, and you got a triple star billing. Very, very significant. Okay, and the code also it explains triple star means is less than 0.001. A double star means greater than 0.001 but less than 0.01. And a single star means between 0.01 and 0.05. And a simple dot means between 5% and 1%. And no billing, okay, if it is between 1% and 1. Okay. So these are all some of the nuances in the analysis. Okay. I think pretty much summarizes what I want to do, what I want to say about a simple linear regression. Okay. The basic graphics important. If you want to publish a paper, editor likes graphics. Can you put everything in graphics? It's much more easily interpretable. Okay. All right. So what I'm going to do now, okay, I can type up R squared. I can type up R squared in one of the corners. You just follow the legend function. Okay. All right. So what I'm going to do is go back to my notes. I want to do what is called confidence bands. Okay. Let me see. I don't need this graph anymore. Oh, maybe I need it. I'll keep it. I'll keep it and let me go back to my notes. Okay, you can see my notes now.
Yes, we see it.
Very good. And I talked about all these things. Whatever I did here is nicely summarized in my R editor. Okay, inference, residuals, R squared, and all those things. Check normality and homoscedasticity. Okay. Okay, maybe I talk a little bit about that one. And the height is a significant impact on FEV. The estimate of beta 1 is significant. Height is a significant predictor of FEV. I told you about the interpretation of the p-value and the goodness of it. Okay, what exactly is the definition of R squared? Okay, this is some technical thing. Okay. Okay. And you need to see the model involves normality assumption and homoscedasticity. What if the normality assumption is not valid? Mind you, p-values and testing depend on the normality assumption. Look for other predictors for a transform the data. And the people ask me, what should be an acceptable R squared? Is there any threshold value of R squared one should be contented with? One should be happy with? There is no threshold value. One can test the null hypothesis that the population R squared equal to 0. We have a p-value associated with the null hypothesis 1.797 times 10 to the power of -9, and to reject the null hypothesis, we can say that observed R squared is significant. Okay. Their curiosity and so on. Okay. I want to talk about a confidence and prediction bands. Okay. We have a boy in the age range 12 to 14. We measure his height, call it as X. We can plug in this number into the prediction equation to predict his FEV. We can also build a 95% confidence interval for the mean of FEV of all boys with the same height. In other words, in the subpopulation of all boys with the height X, find a 95% confidence interval for the average. Okay, we can do this for every imaginable X. We can use R to build a 95% confidence band around the fitted regression. Okay. Let us do this data. Okay. So what I do, Okay. Okay. And home and a copy. Okay. This is my notes, isn't it? Let me minimize it. Okay, let me go back. Climax. Build a 95% confidence band. Around the fitted line. Okay. So let me paste it. Okay. I would like to use a different name, MB2. I already used MB1. The R function is predict. The input is MB1, the regression. And new data equal to FEV, and the interval is equal to confidence interval. Okay. So let me run this. Okay. There's no number here. Actual R function. Let me run this. So it is not working. Let me see. MB1, I think, is input, that's fine. And new data equal to, etc. So it's not recognizing what new data is. So there may be some problem. Okay. Maybe suppose I type new data equal to, say, let us say MB. Let us see what happens. Okay, it works. I want to bring in both them. Okay. And what happens is, let us look at the output. You simply type MB2. Okay. You know, you have a 12 heights. Remember the data? If you remember the data, you have 12 heights. At the height 134 centimeters, what is the predicted value of FEV? Let me write it down. At a height equal to 134 centimeters, what is the predicted value of FEV as per the model? And it is 1.562821. You might ask me, what does it mean? Well, do you remember I wrote the prediction equation? Okay, I wrote the prediction equation. This is. So what I'm asked, this is my prediction equation summarizing the data. I have a boy, 134 centimeters. As per the equation, what is FEV? Plug in. Height is equal to 134. Simplify. And that's the predicted value of FEV. That is 1.56282. The second boy, his height is 138 centimeters. What is the predicted value of FEV as per the model? Plug it in and simplify it. And the FEV predicted is 1.7680865. And for each then you get a confidence interval, 95% confidence interval. Lower limit is 1.417 and upper limit is 1.708. Okay, good. Yeah. So, and that's how the numbers and the 95% confidence interval for the mean. What is the mean now? The population mean, beta 0 plus beta 1 times prediction interval, 95% confidence interval for the mean, beta 0 plus beta 1 times height for every height in the data. That's what it is given. Okay. And let me explain. LWR, lower limit of the confidence interval. Okay. And UPR is the upper limit of the confidence interval. Good. So the R is able to do all these calculations. I can do it by hand also. It will take forever. Now, draw the band on the scatter plot. Okay. So we have to use another R function. Can't remember what it is. Let me look at it. Let me look at my notes. Okay. And that's what I got, 95% confidence interval, etc., and so on. And there is something called the prediction intervals. Okay, I'll come to that little later. And the function is, okay, mat lines, matrix lines. Okay, the function is the matrix lines and a copy and then minimize this. I want to draw the confidence band. Okay, and edit and paste. Okay, let me do one thing. Okay, the function is a mat lines because you know you have 3 columns. You want to plot all the 3 columns. The first column is the line. You already have it. Okay, the other 2 are the confidence bands. Mat lines, the height. Okay, and this is MB2. Okay, my X value is height. Okay, the X values are the height 134, 138, 142, and so on. And you have 3 of them. Okay, okay. Observed height. These are the predicted FUVs. I chose a line type. Let me show you something. LTY is equal to line type, okay, which is equal to 1 is unbroken line. And this is the default. Okay. And if you look at LTY equal to 2 means dashed line. Okay. And I would like to change the colors. You already, maybe let me try this one. What happens? Because I think this is fine. Okay, let me make it as magenta. Okay, the first one is magenta. Okay. And let me make it as blue. The middle one as blue, which already have. And the last one is magenta. Okay. Let us try, see how it works. Run it. I got the band. Okay. I got the band. This is a 95% confidence band. Okay. And let us see. So we have a 95% confidence band. For the mean means of FEV, for the means of FEV at different heights. Okay. And now I would like to talk about what is called prediction, 95% prediction band. Okay. All right, what I would like to do, I just want to keep it. I want to provide a legend later. And let me go back to my notes. Okay. Okay. The prediction intervals. We have a boy in the age range 12 to 14. We measure his height, call it X. We can plug in this number into the prediction equation to predict his FEV. We can also build a 95% prediction interval. What does it mean? Look at all boys with the same height X. Could be 134, 132, whatever it is. Look at their FEVs. It's a subpopulation of all those boys with the same height. Okay. Look at the subpopulation. It is a normal distribution with the mean alpha plus beta x sigma. I should have used beta 0 plus beta 1x. Find the limits of the distribution so that 95% of these boys has FEV within this. Such an interval is called a prediction interval. You look at the distribution. the center of gravity is alpha plus beta x. You find a lower limit and upper limit. 95% of this distribution is between these limits. Such an interval is called a prediction interval. See the contrast between the confidence interval and the prediction interval. We can do this for every imaginable x. We can use R to build a 95% prediction band around the fitted regression. Let me talk about a confidence interval. See the contrast. Okay. We have a boy in the age range 12 to 14. We measure his height, call it as x. We can plug in this number into the prediction equation to predict his FEV. We can also build a 95% confidence interval for the mean of FEV of all boys with the same height. In other words, the subpopulation of all boys with a height x, find a 95% confidence interval for the average. In the other case, I'm talking about the distribution. This is the average. We can do this for every imaginable x. Okay. And let us look at the prediction interval. So let me copy this one. Okay. And a copy and go to my R editor, right? Now I have to do it, right? And edit and paste. So MB2, now call it as MB3. Predict new data equal to, put the whole data MB. And the interval, you simply say double quotes P. P means prediction interval and the C means confidence interval. Okay, run this. Oh, sorry. This is MB1 as input. Run this. Got it. And let us look at the output MB3 and run it. Lower limit, upper limit. Okay. Plot the prediction band. Plot the prediction band, and the function is matlines. Matrix lines. The first entry is my x variable, height, and the second entry is MB3, this folder. Okay, and the third entry is a line type equal to, and I choose 1. The middle one is unbroken line. I can choose 3, 3. Outer lines 3, 3. Line type. And I can choose color equal to little c. Outer lines, I've already chosen magenta. Maybe I can choose red, comma. The middle line is blue. I'm not going to change it. And the outer line red. Okay. I think they are in a pretty good shape. I need another bracket to match with the bracket right after mat lines. Run it. Done. That we have. My color, something has gone wrong. Okay. The middle line is a prediction line. And the two lines surrounding the prediction line is 95% confidence band. and the other is a prediction band. Okay. And I can introduce, I can put some legend, and I'm eager for interpretation. Clinical interpretation. Okay. So let me minimize this and let me go to my notes. Okay. I got this, I had a nice legend. Regression line is the middle one, 95% confidence band, the red one, and 95% prediction band, the magenta. The interpretation, clinical importance. So this graph can be used as a diagnostic tool by a medical doctor. A boy comes for the annual checkup. The clinician wants to check his lung function. The boy blows into a tube. You measure FEV. You measure his height. Check where the point height and FEV falls in the confidence band graph. Where it falls. Okay. He has his graph in his drawer, right? Suppose 3 scenarios. You have a boy 1, height is 145 centimeters. He wants to check whether his lung function is normal or not. He need a graph like that to make a judgment. He blew into a tube. His FEV is 2.1 liters. Boy 2, 155 centimeters, taller, and he blew into the tube. His FEV is 2.6 centimeters. The question for the pediatrician, are their lung functions normal? Mark the points on the graph. Start the graphs all over. Okay, my time is running short. You can practice this one. I marked everything. And here. The boy with 145 centimeters height, his point is there. His height and what is the actual FEV. The boy with 155 centimeters height, his point is there. Okay, his actual height and what his FEV is. And the boy 168 centimeters, that's the point. Okay, the clinician will say, boy 1, your FEV falls within the 95% confidence band. Your FEV is within the 95% confidence interval of the mean of FEVs of all boys with your height. You are close to the mean. Your lung function is perfectly normal. Boy 2, your FEV is not within the 95% confidence band, but within the 95% prediction band. Your lung function is like the lung function of 95% of boys with your height. Okay. I said it's perfectly normal. I say it's normal. Boy number 3 is completely outside the band. Your lung function is not normal. That's the interpretation. Okay. So if his data falls within the 95% confidence band, perfectly normal. If this data point falls within the prediction band, normal. If it falls outside, it's not normal. Okay. For boys with a height of 168, I would expect his FEV to be in between the prediction limits. It is below. For lung function, is not normal. You have problem, boy, you have problem. And that's what it is. Okay. I think, I've achieved what I wanted to do today, especially the confidence bands and the clinical importance. Okay. I have a whole book. The boy or the girl comes for annual checkup. How does the pediatrician know he's growing normally? He takes a lot of measurements. You look at the middle finger. He will measure the length of the middle finger. And he has a graph in his draw, like the graph I produced. He will check whether the length falls within the 95% confidence band or 95% prediction band. If it does, it's, oh yeah, the finger is growing normal. Don't worry about it. I have hundreds and hundreds of such graphs. A graph simple linear regression model, and pediatricians use all these graphs to check whether a particular boy or a girl is growing normal or not. Okay, guys, that's all I had to say for today. And tomorrow, I will talk a little bit about the transformations and talk about what is called categorical regression. I'll bring in some more nice examples to discuss. Okay?
Very good. Thank you, Dr. Rao.
Yeah.
We have a few minutes if there's questions in the chat
Yeah,
box.
sure. Oh, okay, sure.
I see one question. Let me see. Is it possible to integrate R with Python? Then we can draw conclusion.
Oh, you can use Python. Python and R similar. Okay. You know, I have experience with the Python and R. Python is faster. It executes the functions much faster because we have a very, very big data. I would recommend using Python. Okay. But one thing, when it comes to versatility, nobody can beat R. There are 10,000 packages in R. So sophisticated. Every month they keep on adding 2 or 3 packages. Python is not that much diversified. If you learn R, hey guys, you can learn easily Python. No problem at all. You know, if you really want to become a good data scientist, you should learn as many software as possible. Just don't put all your eggs in one basket. Okay? You diversify. I'm giving a training in R. Okay? Whatever I did today, you practice. Take your own data. Mimic me. Do all those graphs and look at the interpretation. I have hundreds and hundreds of data falling in the framework of a simple linear regression. The clinicians use it very much. Okay?
Very good. Thank you. I think the good lesson is FEV is lung function test. So for children's, can you meet? Sorry about that. Can you mute yourself? Okay. So Dr. Rao brought the lung function test as an example. Okay, lung function is related to asthma, allergy.
Oh, yeah, sure.
Lung function, or we call it FEV in terms of percentages, it's a really important variable. So it's clinically relevant. Those of you who in the plant world, you can correlate with plant height with plant yield or seed yield, or in animal feed with milk production. So his example is very general, can be applied to different fields.
Yeah.
So is there any question before we conclude today's workshop? You can unmute and speak out if you haven't typed.
You can what? Yeah.
I don't see any question. Is there any question? Okay. We can conclude. We have 3-4 minutes left, but I think we can conclude today's workshop, and we'll continue tomorrow early morning. I'm sure it's going to be more interesting. So,
Especially students, one piece of advice, practice. Okay. Expertise in a software does not come overnight.
Okay.
I worked on this software so many years. I'm very comfortable. If you want to have a good degree of a comfort, practice. Okay.
Yeah.
That's only the piece of advice I give you.
Yeah, I think that's really important because practice makes you really a complete person. One-time training is not going to change.
True.
And as a statistician or, applied scientist, whatever you do, plan to publish it. Unless you publish it or make it available to others, so your work is not going to be noticed. So that's why you need to collaborate with subject matter specialists, or, as Joseph mentioned, experts, subject matter experts. You are a statistician in methodology, join hand in hand with other field specialists, or, if clinician or breeder or genetist. So that's why you make the team and make it work. So we thank you for today, and hopefully to see you in the morning. Late afternoon, we'll send you the notes for handouts for tomorrow.
Yeah. Sometime in the evening today, I'll send you the second installment.
Yes, and follow the instruction. I think that the notes are pretty clear. You can follow those and write the codes in your own free time, and practice. And if any question, just email to Dr. Rao. I probably send his email with the group, or send me, and I can share with others who is more directly related to your question.
Okay, sure.
Yes, thank you very much, and have a wonderful afternoon, everybody.
And Tess, you can stop the recording, and you can send the recording to the participants.
Yes, the recording will come after this. Probably once we finish the workshop, all the recording will follow up. Okay.
All right. Thank you very
All
much.
right,
Bye,
thank you.
everybody. Bye.
Thank you so much. Bye.
Right.
Bye. Thank you very much.
Yeah, right.
Thank you.
Bye.